So vaporization is the transition from a liquid to a gas, and the opposite transition is called condensation. That's going from a gas to a liquid. So we're going to look at what happens during vaporization. So here we have an illustration of a beaker. We've got all these little Mickey Mouse water molecules in here, and they're moving around because they have some kinetic energy. So we've got a train. We've got our molecules in constant motion. So this is an open beaker. It's open to the atmosphere. Some of the water molecules near the surface may be moving towards the surface, and they may have enough kinetic energy to break free. And then they'll just keep going and escape, right? And so, I think we all understand that if you have a container of water and it's open and you just leave it long enough, all the water will go away, right? It evaporates. And this is where the quote for the chapter becomes appropriate. It's a wild dance floor there at the molecular level. So this is kind of like a mosh pit. Do they still do that? Yeah. So, just a whole bunch of people all moving around really close. So a whole bunch of molecules, right? Really close. Some of them are moving quickly and some of them are moving more slowly because they don't all have the same kinetic energy. The temperature is a measure of the average kinetic energy. Some are moving faster than others. And if you have a fast-moving one that happens to be near the surface, it can escape. But most of them are not going to be able to escape. So average energy increases with temperature. We've got some with high energy and some with low energy. So here, this blue curve would be the fraction of molecules that have this amount of, that have enough energy to escape. And so we'd see that there's a curve here. It's not a perfect bell curve. It tapers out. It draws out long this way. So this would be the amount of energy needed to escape. And this is the fraction of molecules that have that amount of energy. I kind of misread the graph there to start with. So if we increase the temperature of the water, then we're going to increase the average kinetic energy. So the peak of that moves over higher kinetic energy, but it also spreads out more. And so we see from this blue shaded area to the red shaded area, there are a lot more molecules now that have enough energy to escape if they get to the surface. So at higher temperatures, vaporization occurs more quickly. This is also something that you can remember by referencing real life. Why do we put our wet clothes in the dryer? To dry them. Why don't we just leave them in a pile on the floor? Because it's going to take a really, really long time, right? And, you can hang them over something and they'll dry faster, but you put them in the heat of the dryer and they dry very quickly. Why? Because vaporization happens faster at higher temperatures. Because you have more molecules that have enough energy to escape. So I think of this as being like Red Rover. Do you guys know the game Red Rover? At some point I'm not going to be able to use this at all. Anybody heard of Red Rover? Okay, thank you. They don't let kids play this anymore because you could break a wrist or something. But Red Rover, you get a bunch of kids on the playground and you make two lines facing each other with a big space in between, and you hold hands, and then somebody says, Red Rover, send Sally right over. And Sally's like, oh. And so Sally comes running and tries to break through your hands. You can see how people could get injured this way, right? So if Sally has enough kinetic energy, she's going to be able to break through the line, right? Her kinetic energy is going to depend on how big she is, how fast she can run, right? And the line here, its strength is going to depend on how strong these people's grips are holding on, and maybe, their tolerance for potential pain. Some people are like, oh, she's coming at me, I'm just going to let go. Don't want to get hurt. So that's how I view the surface of the water. So we have that surface tension, right, holding the water molecules together there. It doesn't want to increase its surface area. And then you have water molecules moving around. They have to be traveling towards the surface to get out, right? If Sally runs the other way, she's not going to break through the line. She has to run towards the line, right? So the water molecule has to be moving towards the surface, and it has to have enough energy to break free. So at higher temperatures, that vaporization will happen faster because more of the particles have enough energy. Does that make sense? Another way to increase the rate of vaporization is to increase the surface area. So at the surface, the molecules have fewer neighbor-neighbor interactions. So if you get more surface area, you can get more vaporization. It's also because the surface is the only place you can evaporate, right? If you try to evaporate into the side of the beaker, it's not going to work out very well. You're not going to get loose. We also know that liquids that have stronger intermolecular forces evaporate more slowly. So there we've got our kids holding hands in the Red Rover line, except maybe these are football players, right, from the high school. It's going to be a lot harder to break through those guys, right? So if your intermolecular forces are stronger, the liquids will evaporate more slowly. So we have two qualitative terms that we use, volatile and non-volatile. And if you remember, we did an experiment 6A, where we determined the molar mass of a volatile liquid. Volatile means that it vaporizes easily. Non-volatile means it doesn't vaporize easily. So can you think of a liquid that just evaporates really, really slowly? Well, that would be fast. Acetone would evaporate quickly. Slow. Oil. Yeah. Yeah, if you have like a pan of oil on the stove, you could probably let that sit there for years and it wouldn't evaporate. Right? Oil is nonpolar. It doesn't have the stronger intermolecular forces, but the molecules are long and large, and they tangle around each other, and so the rate of evaporation there is actually very, very slow. Whereas things like alcohol, acetone, those evaporate very quickly. Gasoline, right? Water evaporates, was kind of in the middle. So there is energy involved in vaporization. There's energy involved in closing doors to keep the sound of noisy students out. So let's think about that beaker. If we have a beaker that's thermally insulated, what happens to the temperature as molecules evaporate? I think the natural response would be, well, nothing. Why would the temperature change? But what kind of molecules are leaving? Is it the high energy ones or the low energy ones? It's the high energy ones. So we've got all the high energy molecules leaving, the low energy molecules stay behind. What does that do to the average energy of the water? It lowers it, right? So the temperature will fall. And this is why your body sweats, right? Because when you sweat and the water evaporates, it takes energy to do that, and so it cools your skin. Vaporization is an endothermic process. Another way to remember that is, well, how could you make evaporation happen faster? You heat it up, right? Again, the clothes dryer. So evaporation is endothermic. That means that condensation is exothermic. This is not very obvious. If you've ever had your hand over a pot of boiling water, you know that steam can give you a really bad burn, right? You're like, oh my goodness, that's hot, right? It's hotter than just sticking your hand in something of the same temperature, because what happens is your hand is cooler and the steam condenses on your hand, and when it does, it releases a lot of energy. This is a graphic or a table that I made up. It's not in the book. So I looked up average daily temperatures in July. This is from 1971 to 2000 in Fresno, California, and San Francisco. So San Francisco is a little bit north of us, but not enough that it should have a different climate, and yet it does, right? So highs and lows in Fresno, 96.6 and 66.1. It's like 30 degrees difference. In the course of a day, in San Francisco, high of 68, low of 54. Small range. It almost never gets really hot in San Francisco. It also almost never freezes, right? Here we sometimes get down to like 25 degrees and the farmers lose their oranges and it's a disaster. So what causes this difference? It's water, it's humidity, vaporization and condensation. San Francisco is surrounded by water, the ocean and the San Francisco Bay. And so the water will evaporate as it receives heat from the day, and then it will condense when the day cools off, and as it condenses, it releases that energy back. Here in the valley, this is a desert, even when it's not a severe drought situation. We have no large bodies of water, the humidity is low. And so we don't have that water to moderate the temperature. Any questions? I like these topics because they actually sort of relate to real life. They seem more useful somehow. Well, of course, if there's energy involved, we could, measure it. So this is called the heat or enthalpy of vaporization. So delta H, VAP for vaporization. That's the amount of heat needed to vaporize 1 mole of liquid at its normal boiling point. So we can write a chemical equation for the vaporization of water, H2O liquid, going to H2O gas, and the enthalpy for this reaction, which is the heat of vaporization, 40.7 kilojoules per mole. Heat of vaporization is always positive because vaporization is an endothermic process. It depends on temperature a little bit, and that's why this is specified at its normal boiling point. Here, if we look at water, the normal boiling point is 100 degrees Celsius. At the boiling point, heat of vaporization is 40.7. At room temperature, it's 44. So a little bit higher, but not really a big difference. And then you can look at isopropyl alcohol. That's what they rub on your skin before they give you an injection. Acetone and diethyl ether, and these have lower heats of vaporization. So they'll evaporate more quickly. So when a substance condenses, that's the opposite of vaporization. There's an energy change. We can't make or destroy energy just by doing the same thing back and forth, back and forth. The energy that's released is the same amount per mole as the energy absorbed. So we don't call this the heat of condensation, but it is the heat of vaporization with a negative in front of it, because this is the reverse of the evaporation equation. So we can use the heat of vaporization as conversion factor, just like we did heats of reaction. It's this amount of energy for the molar amounts given in the equation. So calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. Well, the thing we're going to need here is we're going to need the heat of vaporization, which is 40.7 kilojoules per mole. So the heat of vaporization for water at its boiling point is 40.7 kilojoules per mole. Okay, so this is just dimensional analysis. So we need to look at the numbers, right? What are we given? Well, we're given this amount of kilograms, 2.58 kilograms of water. That's the only number that we are given. And then it's asking us to calculate the amount of heat in kilojoules. So my path is going to be going from kilograms, something, 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 to kilojoules. And we have to figure out what units are going to come in between. This is a clue right here. This relates kilojoules and moles. So if we knew how many moles of water this was, this would be the conversion factor to give us kilojoules. So we've got kilograms. How do we get kilograms to moles? Go to grams first. Change it to grams, and then we can use the molar mass. So it was 2.58 kilograms of water, and I've got 3 arrows. So I'm going to have 3 conversion factors. His dimension analysis strikes again. Kilograms to grams to moles to kilojoules. Kilograms to grams to moles to kilojoules. Writing that path out is the essential part. So I'm going to divide by kilograms here, so those units cancel. Here I'm going to divide by grams. Here I'm going to divide by moles. We're using the units to tell us what to do. So here I need the conversion factor between kilograms and grams. And some students continue to struggle with this and get it backwards. There's still time to fix that. There's still an exam and a final exam left to use it, right? So if you struggle with this, ask yourself, well, what does K mean? Kilo. Kilo stands for times 10 to the third. That's what it means. It's like an abbreviation and a nickname for times 10 to the third. So here I have kilogram. On the other side, instead of writing kilo, I'm going to write what it means. So I'm going to write times 10 to the third. Well, I've got 1 times 10 to the third grams is equal to 1 kilogram. Works every time. Grams to moles, molar mass, right? So this is not about how to calculate the molar mass, so I'm just going to put in there 18.02 grams per mole. This is what the topic is here, kilojoules per mole. That's the heat of vaporization. We don't have a chemical equation here given to us, but we understand what the heat of vaporization is. So 40.7 kilojoules per mole. And let me grab a calculator. .58 times 1 AE3 divided by a train whistle, 19.02 times 40.7. Whole bunch of digits my calculator gave me. How many sig figs should that answer have? 3. Our starting number had 3, right? And our conversion factor here had 3. Good grief, what are they doing out there? So, should I round this to 583 kilojoules? I need to add a 0 here. So here I'm rounding in the tens place. If I'm rounding in the ones or in one of the decimal places, I'm okay. I don't have to be worried about it. But when we round to the tenths or higher, we can sometimes end up changing the number drastically. I'm going to round 500,375,000 to 5. Yeah, that's not the same, right? So this would be 5830 kilojoules, or the safest thing is to put this in scientific notation and then round it. So 5.83, that 2 rounds up, and then what am I doing with my decimal place? 1, 2, 3 places, times 10 to the 3 kilojoules. Any questions? Well, we just talked about evaporation in an open beaker. What if the container is sealed? It's not open. So here we're looking at an Erlenmeyer flask with a rubber stopper in it. So water is going to evaporate, and the rate of the evaporation depends on the temperature, right? If it's hotter, it evaporates faster, and on the surface area. More surface area evaporates faster. When you're using those silly blow dryers to dry your hands in the restroom, why do you rub your hands together? To spread the water out and make sure you've got the maximum surface area, because it'll evaporate faster. So here, the surface area is not changing as this water sits in this flask, and the temperature is not changing. So here we have evaporation, right? So we've got evaporation. Originally, there are no water molecules up here to condense, right? But as some of these evaporate, now we start getting water molecules in the gas state, and these are zipping around, bouncing into things like gas molecules do, and they're going to occasionally hit the water and get trapped, right? The rate of condensation is going to depend on the concentration of particles here, or the partial pressure of the gas. You get more particles there, condensation is faster. Does that make sense? So these two things are going to go on. The evaporation is going to continue at a constant rate. As we get more and more gas up here, the rate of condensation is going to increase, and that'll keep increasing until we reach a dynamic equilibrium where the rate of evaporation is equal to the rate of condensation. And so we've got things evaporating and things condensing, but if you look at the number of gas molecules up here at any time, it's the same. It's not the same gas molecules, but it's the same number. Any questions? So this is looking at those rates on a graph. So this is increasing, going up as time goes on. The rate of evaporation is just going to stay constant because the temperature isn't changing and the surface area isn't changing. Nothing's changing there. Initially, the rate of condensation is 0 because there's nothing to condense. As evaporation proceeds, we get more and more gas, and so the rate of condensation increases until they become equal. Dynamic equilibrium. So the vapor pressure of that gas is the pressure of a gas in dynamic equilibrium with its liquid. So it's the partial pressure of the gas when it's in a sealed container in equilibrium with its liquid. Okay? The vapor pressure will depend on the intermolecular forces. If the intermolecular forces are weak, this rate of evaporation will be higher, right? If the intermolecular forces are strong, the rate of evaporation will be lower, and they're both going to come to the same place. So weak forces, high vapor pressure. So here we have a system in dynamic equilibrium. It looks like that's maybe pentane. So here we have the liquid, and some of it's evaporating, and it's reached equilibrium, and so the rate of condensation is equal to the rate of evaporation. And so the molecules are basically taking turns being in the gas state, and then they're switching off. If we pull up on this plunger and increase this volume, what does that do to the pressure of this gas? It lowers it. A lower pressure means that your rate of condensation is lower. So now the rate of condensation is lower, the rate of evaporation stays the same. So this will continue on until we reach a new equilibrium. We can do the opposite. We can push down on this and make this a higher pressure, a more concentrated gas. Then the rate of condensation will increase, while the rate of evaporation just stays the same. So this is known as Le Chatelier's principle, that when you disturb a system in equilibrium, it's going to respond in a way that will minimize those disturbances. So at equilibrium, the pressure of this gas will be the same, regardless of whether it's in a big container or a small container. The vapor pressure is the same. So what would happen to the vapor pressure of a substance when its surface area is increased at constant temperature? So vapor pressure is the pressure at equilibrium. What does increasing the surface area have an effect on? Does that affect the rate of evaporation? Yeah, it'll evaporate faster. Rate of evaporation goes up. What about the rate of condensation? Is that going to depend on the surface area? Yeah, it will. If you have a lot of surface area, you have a big target for those gas molecules coming in. More of them are going to hit, right? If you have a little, maybe the same volume as this tall, skinny tube with this very tiny surface area, those guys are bouncing around, and the chances of them hitting that surface area, the surface of the liquid, are much smaller. So by increasing the surface area, we're going to increase the rate of evaporation, but we're also going to increase the rate of condensation. So how's that going to affect the vapor pressure? The same. It'll be the same, which is very convenient. The rate of evaporation depends on temperature, and so the vapor pressure will also depend on temperature. So as we increase, here we've got water with this red line. As we increase the temperature, the vapor pressure of the water increases as well, because the rate of evaporation increases and it doesn't really affect the rate of condensation. We can have a small change in temperature resulting in a large change in vapor pressure, where this gets kind of steep up here. Why is that? Well, more particles have enough energy to go into the gas state. This will affect the boiling point. So, I don't know about you, but I think defining what is boiling, right? Well, boiling is when the water is hot and there's big bubbles coming up from the bottom, right? That's boiling. Well, scientifically, what is that? It's the temperature at which the liquid's vapor pressure equals the external pressure. So why are those bubbles forming? There's a pot of boiling water. Those bubbles are water vapor, water in the gas state. The vapor pressure of those is the same as the external pressure. And so bubbles of gas will just appear in the liquid. They're always going to float to the surface because they're much less dense than a liquid. So now it's not just particles on the surface that are escaping, it's actually particles in the interior. A whole bunch of them are like, and they all go into the gas state, make a bubble, and the bubble floats up and pops, right? So what we call the normal boiling point is the temperature at which its vapor pressure equals 1 atmosphere. So the temperature that liquid would boil at sea level, okay, that's called the normal boiling point. That would be 100 for water. So this is a heat diagram. We've got temperature here. This is amount of heat added. And so as we take a liquid and we add heat to it, the temperature goes up. That makes sense? When it gets to the point where it's boiling, the temperature will stay the same while it's boiling. Because what's happening is all that heat that you're putting into it is going away as those more excited, those faster moving particles boil away, right? You're taking all the highest energy particles and they're leaving. And so the average kinetic energy, the temperature of the liquid stays the same until it has all boiled away. Once you've boiled away all the liquid, then the temperature will go up again. You can heat a gas to higher temperatures. So this has significant implications for cooking, right? If you heat a pot of boiling water, what temperature is it? 100 degrees Celsius. Well, what if you let it boil for 10 minutes instead of 5 minutes? Does it get hotter? No, it doesn't. And that doesn't really make sense, does it? But you're just once it starts boiling, it's not going to get any hotter. Because the energy that you're putting in, we have liquid particles escaping into the gas, and then those leave, and so the average kinetic energy of the liquid cannot increase until it quits boiling. So, boiling point is where the external pressure is equal to the vapor pressure of the liquid. That's when the liquid will boil. So looking at this same chart from a couple slides ago, up here we have 760 torr. That's normal atmospheric pressure. At that temperature, the vapor pressure of water is 760. I'm sorry, the temperature of the water at that pressure is 100. So at 100 degrees, the vapor pressure of water is equal to 1 atmosphere, and the water will boil. Ethyl alcohol will boil at a lower temperature because its vapor pressure will get to 760 torr sooner, and diethyl ether will boil at an even lower temperature. So we can estimate the boiling point of water at an external pressure of 200 torr. So this is 200 torr. And so what we need to do is draw a line. We're going to draw a line. We'll try to make it a straight line. So where does the vapor pressure of water equal 200? Right here. So we can drop another line down there. And this is a multiple choice question. And so it's clearly not 84. It must be 66. At a lower pressure, water will boil at a lower temperature. I don't know if you've ever noticed especially on like cake mix boxes and stuff, there's high altitude directions. So if you live in Denver, elevation's a mile, right? Like 5,000 feet. The air pressure is less there, the atmospheric pressure. So if atmospheric pressure is less, then water boils at a lower temperature. Well, the temperature at which you cook your food affects how fast it gets done, right? So if your stuff is boiling at 90 degrees instead of 100, it's going to take longer. So you have to adjust the cooking time. And the same thing goes with baking. Any of you guys have an Instant Pot? Do you know what the Instant Pots are? So, true confession, my husband does all the cooking. He does all the cooking. We have an Instant Pot and he uses it all the time. So the Instant Pot is the new fancy version of a pressure cooker. You can use it like a crock pot, but it also has a valve where you can seal it. When you seal it, as it heats up, the pressure builds up. So if I'm at a higher pressure, the water can get hotter than 100 degrees Celsius. That means the food cooks faster. Because anything that has water involved with it, when you get up to 100 degrees Celsius, it's not going to get any hotter until all the water has evaporated. So that limits the cooking. That's why we use fat for frying, because you can heat oil to a much higher temperature and you can cook things faster, right? You can't make French fries in boiling water. Doesn't happen. So as we see from that graph, the relationship of vapor pressure and temperature is not linear. Let's just go look at that again. This is not a straight line. Come on, pointer. This is not a straight line. None of them are. Here's ethylene glycol. That's what's in radiator fluid, antifreeze. So it's not a straight line. It's exponential. And this is the equation for it. We can rearrange that equation into a linear form, and that's known as the Clausius-Clapeyron equation, so named after two scientists. And we're not going to go into the details of that. But using this equation, this is in the form of a line, y equals mx plus b. So here we have y, the natural log of the vapor pressure. The slope will be negative heat of vaporization divided by r, the gas constant. 1 over t is our x. So we're graphing natural log of p versus 1 over t. And then this would be our intercept, which we usually don't care about at all. So we can graph data, and we can get a slope of negative delta H over R. So we can actually, by measuring the vapor pressure at different temperatures, we can calculate what delta H is. So this is the kind of graph that would be made. Here's the natural log of the pressure, and this is 1 over the temperature, and of course it has to be in kelvins. And then they use a computer to do a linear regression line, and the slope of that line is negative 3478 Kelvin. So that's equal to negative heat of vaporization over R. So we can rearrange that and say, well, heat of vaporization is equal to negative slope times R. And so we can calculate what heat of vaporization is. This is not the kind of a question I'd give you on an exam, because you need like a computer to do it, or a really fancy calculator, graphing calculator, because you have to graph this stuff, right? So what you would do is, here we have the temperature. You're going to calculate the inverse of the temperature. So, this is 1 over 255. You find the decimal equivalent of that, and you do that for all of these. And we need the natural log of the pressure. So we're going to have the natural log of 11.3. And then this is going to be your y variable, and this is going to be, I'm sorry, not that one, this one. There's your y variable, and here's your x variable, and you get the slope, and you can calculate delta H from the slope. We can also get a 2-point form of the equation, which is nice because then we don't have to graph anything. So here we have 4 variables. We have pressure 1 and pressure 2. We have temperature 1 and temperature 2. And we have the heat of vaporization. I guess you could say that's 5. So if we know the temperature and pressure for one thing, and we know the heat of vaporization, then we can calculate the pressure, the vapor pressure, at a different temperature. Or if we have the pressure and temperature at 2 points, we can calculate delta H. So this is the kind of equation or kind of problem that could happen. Propane has a normal boiling point of 42 degrees Celsius and heat of vaporization of 19.04 kilojoules per mole. What is the vapor pressure of propane at 25 degrees Celsius? So this is the equation that we're going to need. So let's just write that down before we forget. Any questions? So we've talked about vaporizing a liquid in an open beaker and in a sealed container. What if we do this in a sealed container with heating? So this is like the Instant Pot. So as the temperature rises, so does the pressure. The gas is going to become more dense, the liquid becomes less dense, and at some point, the gas and liquid states are going to merge and become what's called a supercritical fluid. So this is peeping into a vessel, and here we can see the division between gas and liquid. And as it heats up, the liquid is becoming less dense, the gas is becoming more dense, and at some point, that division just disappears. It's not that all the liquid became a gas or all the gas became a liquid, but they have merged into the same state, supercritical fluid. That can only happen above a critical temperature. So TC, critical temperature, is the temperature at which a supercritical fluid forms. Above that temperature, you cannot have a liquid. The pressure that you have at that temperature is called the supercritical pressure. So supercritical fluids are really useful as solvents. Supercritical CO2 is what they generally use to decaffeinate coffee, remove the caffeine without removing all the compounds that make the coffee taste good. And then, do we have a lot of toxic waste from this solvent? No, we have carbon dioxide, which of course, too much of anything is bad, but carbon dioxide's a lot better than like, benzene or something.